and welcome back to Chapter 17. We're going to talk a little bit about cloud formation and the behavior of humidity in the atmosphere and ways in which we can physically work on changing the humidity in a system, and also talking a little bit about heat and how it's lost from the system. Ultimately, what do these lead to? They lead to us talking about weather and severe weather, but for right now, we're going to focus mainly on moisture and its behavior with regard to cloud formation. Adiabatic temperature change is the first topic of interest here. Then we'll talk about methods in which we can get that adiabatic temperature change to occur. And then once we've talked about adiabatic temperature changes, we'll talk about the different ways in which the adiabatic temperature changes, which we call lapse rates or rates of temperature decrease as pressure decreases. In general, we know that there's a basic relationship between pressure and temperature in a system, and if we want to increase the temperature in a system on something, we can actually increase the pressure in the system, and if we want to decrease the temperature, we can decrease the pressure. There are a number of different equations in chemistry and physics that will relate pressure and temperature in of a system or of an air parcel in this way. And so if we start out at the Earth's surface, and I'll draw the surface down here at the bottom, and we start out with, let's say, a little balloon, and this balloon down here is, let's say, at 10 degrees Celsius here, okay, and it's sitting at almost an elevation of sort of, let's say, is at 100 feet, right? So we know that the pressure here is high. Why do we know that? Well, because we know that the pressure in the atmosphere decreases as you move away from the Earth's surface. And so what's going to happen then if we take this balloon and we let it rise up? It's actually going to get bigger, isn't it? Why is it going to get bigger? It's going to expand because at higher elevation, so let's say we've gone up to, let's say, 500 feet, okay, there's less pressure holding the balloon together, right? Less pressure holding the balloon in its shape or in its form. And that's going to have an effect on temperature. Expanding the balloon separates the molecules, and so you have fewer molecules. If you were to put a thermometer into this balloon, you'd find the temperature decreases a little bit. So let's say it's now at 5 degrees Celsius. So going from low elevation to high elevation will lower the temperature in a system, in a parcel of air, or in this case, we have a balloon. And the reverse will happen if we take the balloon back down. So let's say we come to the right. On the right side, we have a very big balloon here. Let's say inside it's at 2 degrees Celsius, and we push it down towards the Earth's surface. Don't worry about why we would do that. It's going to get really small, and as it gets small, because the pressure increases 15 degrees Celsius. So pressure increases as you come back towards the Earth. Now, you also have the issue of temperature change as you get closer to the Earth also increases, but this is purely pressure-driven temperature change, and so that's by definition adiabatic temperature change. Right? Normally, if you think temperature change is happening, you think it's because we're losing heat from the system. Heat is lost. Okay? But this is temperature change in which heat is not lost from the system. The amount of heat here at the ground surface is the same as the amount of heat up here. Okay, Okay, so the amount of heat in the system is the same. We haven't lost any heat from the system. We've just changed the volume of the system, and that has caused, depending on where the balloon is moved, if it's moved up, it's caused cooling, and if it's moved down, it's caused heating in the system. And it's this kind of vertical motion that ends up creating a lot of severe weather that can account for, supercells and tornadoes and even hurricanes. So here's a diagram. It's a little bit more sophisticated, but it includes a slightly new concept as well. So what we end up seeing is that the parcel of air down here at the bottom starts at 32 degrees Celsius. It's going to rise up, and it's going to rise up till it hits some particular level here. In this case, it's at 2 degrees Celsius. That's a function of the amount of water in this parcel. So this circle represents our parcel of air. And the condensation level is also saturation. So what happens at saturation? We see cloud formation. Okay, so that means that we're going from a vapor, right, to droplets. Okay, so clouds are simply micro or really small droplets of atmospheric moisture that have collected or condensed into a liquid, but they're light enough and small enough to be hanging out up in the upper parts of the atmosphere. And so at saturation, as things cool down, as air parcels rise up, we see cloud formation, and that's a key. Okay? Now, I'm going to come back to this later on. The adiabatic temperature change here, right? How fast the temperature changes, that's the rate of temperature change. And the adiabatic temperature change here are a function of whether the air is dry. So that doesn't mean it lacks moisture or lacks H2. It means it lacks clouds. It's not at saturation. So under wet conditions, here at the top, it's under saturated conditions, and under dry conditions, which isn't really dry, it still has water in it. It's just, there is vapor. It is under saturated conditions. Okay, and those two rates are different. Okay, notice if it's dry, we can lose 10 grams, excuse me, per kilogram. Sorry, 10 degrees C. 10 degrees of temperature per 1,000 meters. And if it's wet, we lose 5 degrees C per 1,000 meters of elevation change. And so that means, if you're here at 32 at the surface and you go up using this dry rate of change, it means you're going to take away 10 degrees of temperature per every 1,000 meters that you rise up. And so at 1,000 meters, from 0 to 1,000, you go from 32 minus 10 gives you 22. If we're at condensation or saturation level, we're at 2, but the rate here now is going to change, and we're at 5 degrees C. So we're going to rise up, and we're going to take 2 minus 5 gives us negative 3. And if we went from negative 3 to negative 8, we'd also be taking away another 5. And again, from negative 3 to negative 8, you're rising up 1,000 meters. So the wet and dry rate are different, and that means that sometimes we'll have clouds in the atmosphere, and sometimes we won't. There are a number of ways to make clouds, right? And that's what this next thing is about. Cooling air increases relative humidity, right? That's what we just talked about in the first introductory segment. So we reach condensation, or we increase the humidity to saturation. At saturation, we see cloud formation because the relative humidity in the system has reached 100%, and so clouds, at least in those little parcels, are able to form. So the question then is, how do we get air to move up and down, right? That's what this next segment is really about. The vertical movement of air through the atmosphere, or a parcel of air through the atmosphere. Orographic lifting refers to the use of topography as a natural way to push atmospheric air up to higher elevations. And I'm drawing on this top diagram here in blue up to the tops of these peaks. So we have atmospheric air parcels coming in from the coast. They're at the coast. They've picked up moisture from the oceans. They move on land up. As they move up, what happens to the pressure? Pressure decreases. Pressure goes down, right? As they move up, what happens to temperature? Temperature goes down. Okay. As temp goes down, what happens to relative humidity? Relative humidity, or RH in this case, goes up. And you end up with rain commonly, or precipitation on the front side of the mountains and the formation of clouds. Now, as they go up to the top, precipitation continues. It means they're losing moisture, and there's no air in place in the mountains for them to pick up new moisture or additional moisture. And so as they come across to the dry side, it means they're lacking the necessary moisture to produce rain. And as they're coming down in elevation, what happens to pressure? Well, as they go down in elevation, pressure goes up. What happens to temperature? Temperature goes up, right? And what happens to relative humidity as the temperature goes up, but we don't change the moisture in the atmosphere? The relative humidity goes down in that system. And so that means you cannot produce rain. And this is why places like Nevada, Arizona, parts of Wyoming, and Idaho are dry, because the coastal air regions received most of the moisture that was brought inland from the oceans as the atmospheric sort of conditions pushed the wind up and over the mountains. And so in the Sierras, it's really stark. On the left-hand side here, you see redwoods and ferns. And on the right-hand side here, you see a desert region, which is very, very dry. And that's orographic lifting. Okay. Now, there's a couple other ways that this can happen as well, and they're related to sort of thermal heating, which is we're going to refer to as convection. When we have thermal heating of the land surface, so the sun's rays come in, that heats up the land. The land then sends out our long wavelength infrared, right, to heat up the air. And what happens to the air as it heats up? It expands and becomes less dense and rises up. As it cools, then it will come back down. So this is more dense. So this is buoyant, and it's hot. And this is less buoyant, and it's cool. Okay? And so it's sinking. Right? And so that's what we're seeing here is this parcel of air rises up. Its condensation level forms clouds. Now, there's another thing here called convergence, and this is a little less clear. But basically what happens is if you have air, I'm going to draw this on the top right-hand side here, air coming in from the right and air coming in from the left along the Earth's surface. So if we just draw on the Earth's surface here. Okay, so there's the surface. Those two air masses are going to collide potentially, and what's going to happen is they're going to get pushed up like this, right? They got to go somewhere when they run into each other. And so the convergence of air in that way can push materials or push parcels of air up. And that has less to do with buoyancy and a lot to do with just the redistribution or redirection of forces. So in the case of convection, we have hot, buoyant material rising. This is just like a lava lamp, right? This parcel of air rises up, it continues to rise, and then will eventually hit condensation level. And then you have convergence, where basically you have two air masses maybe coming together, or a zone where air is coming together. They don't even have to be parcels of air, just wind coming together from different directions and pushing air up. That would be a way to get vertical movement as well. Okay, so the last one is something a little bit like convergence, but it's a little bit different. It's called frontal wedging. Fronts are parcels of air that have different temperatures and different different amounts of humidity across a common boundary. So on the left-hand side, we have warm air, which is more buoyant and more likely to rise up. And on the right-hand side in this diagram, we have cold, dense air. So this is dense or more dense, and this is lighter. Okay. And so what happens when you get warm air that's lighter or less dense colliding with cold air on the right-hand side? Well, one of them, they're not going to stop at the Earth's surface. One of them's going to go up, and it's the lighter one that heads up. Just like in plate tectonics where the denser rocks have to sink down into the mantle. In this case, the warm moist air is actually less dense than the cold air. And so as the warm air rises, it reaches saturation or condensation. And then clouds form and we end up with precipitation. So we can have convergence, which really doesn't involve packages of air like this necessarily. That could drive vertical motion where basically wind is colliding with other wind and headed up. But we also have like packages of air like this where we have a parcel that is warm and full of moisture and one that is cold and not full of moisture, such as the one on the right side here. Oops, I don't know, my cursor's not working. Okay, on the right side, where'd it go? Here it is, on the right side here. And as they collide, it's going to push up the less dense air. All right, so let's talk a little bit more about these environmental lapse rates, the dry rate and the wet rate. These become important when we start to talk about the kinds of weather that can be produced, right? So ultimately, we started out way back minutes and minutes ago talking about relative humidity. Then we figured out that relative humidity could be changed by changing the pressure in a system, which changes the temperature, and that changes how much water the air can actually hold to some degree. And so that means that we can go from undersaturated to saturated conditions to cloud formation. And now we want to talk a little bit about stability, conditional stability, and unstable environments. So this has a lot to do with how fast the air is going to change temperature as it rises up. So we've got stable conditions, conditionally stable conditions, and unstable conditions. And then we already talked a little bit about that adiabatic temperature change. It's without heat loss, okay? And we have also defined a little bit the dry adiabatic lapse rate. That's the rate of temperature change with elevation. So this is degrees C change per meters, in this case 1,000 meters, and a dry rate, which is degrees C per 1,000 meters. So the wet rate is slower than the dry rate. Okay, and that's an important thing to remember as we're looking at the next few diagrams. So in this particular diagram, we have, again, elevation on the y-axis over here, and then nothing. It's just distance along the x-axis, some land distance or land surface distance. And we're seeing a parcel of air at 20 degrees Celsius rise up, and as it rises up from 0 to 1,000, it's going to decrease from 20 degrees Celsius to 10 degrees Celsius. It does that because the dry lapse rate is 10 degrees per 1,000 meters, and there's no clouds formed here. It drives up one more package, or the same package drives up one more increment, let's say 1,000 meters again. Now we're at 2,000 meters, right? And it's cooled to 0 degrees. Well, it's at 0 degrees, it's at its condensation level, it's at saturation, and clouds form. Now it's going to rise up again another 1,000 meters, but the temperature change here now is different. Down here, the lapse rate was 10 degrees Celsius per 1,000 meters. And up at the top here, every time it moves 1,000 meters, it's actually 6 degrees Celsius per 1,000 meters. Okay? And so below my line, it's rising and decreasing 10 degrees, and above this line I just drew, it's decreasing only 6. What's important to note, though, is that the air in the parcel is cooler than something called the environmental lapse rate. So up in the top left of this diagram, there's something called the environmental lapse rate. That's the atmospheric temperature change we predicted when we defined temperature in the stratosphere, or troposphere even, where you see temperature decrease. Okay, actually this should be temperature and this should be elevation. So temperature is decreasing as elevation increases. So the environmental lapse rate here is that's the natural temperature change, and then this is the temperature change in the parcel. Okay, and this over here is the temperature change in the parcel, the red line shown here. And so what we notice, though, is that the parcel temperatures are always less than the environmental rate. So, if I draw a line from here down, right? Oh, I'm sorry. I'm going to draw that in a slightly different way, I think. All right, let's draw that across. That'll make more sense. And so if I come down here to 1,000 meters, I'll use red here. At 1,000 meters, the environmental rate is at about, 19, 18, right? That's the atmospheric temperature change with elevation. And what's the dry adiabatic rate? The temperature in the parcel. The dry adiabatic parcel temperature is at 10, right? So the parcel is at 10 degrees C, so it's cooler, and the air outside of the parcel is at 18 degrees C, and so it is warmer. As long as the air in the parcel is cooler, it's stable. And that's the key here to remember. In stable air conditions, the temperature inside the parcel is cooler than the temperature outside of the parcel. All right. And so if we flip over to another a similar diagram, we see convective heating going on instead of some sort of wedging process. We see atmospheric moisture forming at the condensation level, right? Just like before, the y-axis shows a change in elevation of 1,000 meters per increment on the y-axis. But what's the big difference here? The big difference is that the environmental rate, which is shown in purple, is always less than, in this case, the wet and the dry adiabatic rate. So both the dry rate and the wet adiabatic rate, the temperatures are always greater no matter what elevation you go to. So here, even let's say you go to 3,000 meters, we draw a line across. The environmental rate right here is around 0 degrees Celsius, and the wet rate, or the wet rate temperature, is about 15. So inside the parcel, the temperature is 15 degrees C. Okay, but outside the parcel, the temperature is 0 degrees. And so whenever the parcel of air inside is warmer than the surrounding air, it's going to be less dense, and it's going to have a positive buoyancy. It's going to be rising up, and so you're going to get a lot of vertical motion caused by this positive buoyancy, and that tends to lead to unstable air conditions. Unstable air conditions are, if you want to just summarize it, they're thunderstorms, right? They're the kinds of conditions that we're going to experience right about now in the Midwest, where we start to see tornadoes and hail and that kind of stuff. And that is caused by the vertical motion or movement of water-laden parcels of air. Okay? All right, so I'm going to wrap this one up. All right, so we've got stable, and we've got unstable, or if you want to think about it, we have absolute stability. And in that case, we're going to see a diagram like this where we have the dry, and then the wet, dry, wet, and then we'll have the environmental, right? Like that. And so under these conditions, if this is temperature on the y-axis, this is on the x-axis, low T, and this is high T. So the temperature in the parcel is always less than the environment. And so that means as it rises up at different elevations, so here's a kilometer, for instance, 2 kilometers. Let me fix that. And then finally 3 kilometers up here, right? The temperature in the environment, it's always a little bit warmer. And so it's always stable. Excuse me. And if we want absolute instability, what is this diagram going to look like? So then we've got low T, high T, and we've got our environmental rate decreasing with elevation like this. So there's E for our environmental rate. And then both the dry rate and the wet rate, wet and dry down here, are going to be higher temperature. So when it's absolutely unstable or unstable, you've got higher temperatures in the parcel because it's more buoyant, and then the surrounding air keeps rising up, and that creates a situation where you can get severe weather. And then you have the last one, which is conditional stability. And I didn't talk about this or show an image of it. I'm just going to draw it now. And conditional stability is a function of really a function of this, like where the initial parcel is in terms of its temperature. But when this whole process of vertical lifting starts, we got low T and we've got high T here. And so I'll draw the environmental lapse rate here first. So there's E for environmental, and then we'll do the dry rate, which sits right on top of it, and then at some point it flips off. So the dry rate in this case lines up with the environmental lapse rate, and so it means the temperatures in this are the same. The decrease in temperature with changing elevation is the same in the environment between the environmental lapse rate and the dry lapse rate. But then the wet rate is going to leave us with a temperature. So this is condensation level right here, right? Okay, so the condensation level, above that condensation level, we form clouds, switch to the wet rate, and that means the rate in the parcel is lower than that of the environmental rate, which means it's warmer than the environmental rate, which means that air above the condensation level will be positively buoyant and cause more vertical motion of the air mass. So we need something physical under absolute stability conditions to push air up. That could be a mountain range, like the orographic effect. So that would be stable air, not necessarily thunderstorms. We could have two fronts coming together, like a warm front, or two air masses coming together to make something like a warm front, which is pretty stable air, not very violent. Under absolute instability, the parcel is warmer than the surrounding air, which leads to buoyancy and doesn't require fronts to create vertical motion. And then conditional stability is a mixture of both of those, where you start out in the dry conditions below the level of saturation and the environmental elapse rate, and the dry conditions are the same. And as you move above that saturation level, the wet elapse rate keeps the temperature or heat in the system, keeps it higher than the environmental rate, and leads to some more violent atmospheric conditions. Okay. All right, so I'm going to wrap this up and just go ahead and stop there with our discussion of condensation levels. We talked briefly about orographic lifting, convergence and convection, and frontal wedging as ways to move atmosphere vertically in the system and to lead to the formation of clouds. In the next segment, we'll talk about how clouds, not how they form, but the classification of clouds and cloud